Hello viewers, welcome to this next lecture on this MOOC course on mathematical portfolio theory. You would recall that so far we have talked about the portfolio optimization problem from the perspective of looking at a portfolio which only involves risky assets, and we started off with an example of two risky asset portfolio, extended to the case of 3 assets and finally to n number of assets, and we looked at how we are basically going to determine what is the minimum variance portfolio, and also we talked about opportunity set as well as the efficient frontier, and we looked at this two fund theorem which basically said that any portfolio on the efficient frontier can be obtained as a combination of two portfolios on the efficient frontier. So, that means that any portfolio on the efficient frontier is equivalent to a combination of two portfolios in the efficient frontier itself, and we determine the weights accordingly. So, now what we are going to do is that we are now going to include the risk free assets. So, earlier when we talked about risky assets, we primarily looked at stocks, but now we want to look at what happens when in addition to n number of risky assets, we also entertain the possibility that we will include, in addition to these risky assets, we will also include a risk free asset in our portfolio. So, accordingly we begin this lecture with this narrative on inclusion of a risk free asset. So, we start off with our introduction of a risk free asset. So far, so we will make the following observation, that so far our discussion has been restricted to portfolios comprising of only risky securities, where the variance of each asset is positive. That means my sigma square is greater than 0. Now, if we take into consideration the existence of a risk free asset that has the variance of the asset, that means the risk free asset, being 0. Okay. So, then we have the following assertion. So, I can say that further we also assume there is the existence of the possibility of borrowing and lending at a risk free interest rate. So, just to sum up what we have done, so far that we are restricted to portfolios comprising of only risky securities and the variance was positive, and now we take into consideration the existence of a risk free asset, and this risk free asset obviously is going to have a variance being 0, and finally we make the assumption of the existence of the possibility of borrowing and lending at a risk free rate. So, this means that when you are considering a risk free asset, this basically means that there is no randomness in terms of its return. So, this means that the return as a random variable is just a constant, in which case by definition the variance is going to be equal to 0. So, we first take into consideration the existence of such a risk free asset, and furthermore we take into consideration the possibility that borrowing and lending can take place, that is in the context of bonds, can take place at this particular risk free rate that we have identified. All right. So, we now consider, so the next thing we do is we now consider, so once we have this risk free asset in the picture, we consider an investment in a risky asset and a risk free asset with the respective weights being W1 and 1 minus W1. Further, the corresponding returns are R1 and Rf respectively. So, here we use R subscript f to denote the risk free rate of return. So, essentially this means that I will have two assets. So, there is an asset say A1 which is risky, and say there is an asset AF which is risk free, and the corresponding weights are W1 and 1 minus W1, and the rate of return is R1 and Rf, and note that here Rf, this is going to be a random variable, but this is going to be deterministic or constant. Okay. So, now you have this portfolio of two assets. So, what you can do now is the following, that we look at the expected return and risk of this portfolio. So, then the expected return and variance of this two asset portfolio are given by, so if I identify the portfolio with the letter P, so the expected return of the portfolio P is simply going to be W1 into expected return of the risky asset plus 1 minus W1 into expected return of Rf, and you just note that E of Rf is simply Rf because Rf is deterministic. And your variance for the returns of portfolio P, which is denoted by sigma P square, you would recall that this is going to be W1 square sigma 1 square plus 1 minus W1 square sigma F square plus twice W1 into 1 minus W1 into sigma 1 F. Now, basically look closely at these two terms in the expression for sigma P square. So, by definition, we will have sigma F square is equal to 0 because the return is deterministic, and also we will have sigma 1 F, which is that because one of the random variables is constant. So, the covariance also is going to be 0. So, that means that this is 0 and this is 0. So, you basically then have, consequently you will obtain that sigma P square is equal to only W1 square sigma 1 square, and which implies that sigma P is equal to W1 sigma 1. So, we will take the positive square root. So, this gives So, just to look back here, so we have sigma p is equal to W1 sigma 1. So, this will give you W1 is sigma p over sigma 1. And then what you can do is we can substitute this in E of Rp. So, hence we will have E of Rp, this is going to be equal to W1 ER1. So, this is going to be W1 ER1 plus Rf minus W1 Rf. So, this can be written as Rf plus E of R1 minus Rf into W1, which then becomes Rf plus E of R1 minus Rf, and for W1 I substitute this by sigma p over sigma 1, which then can be written as Rf plus E R1 minus Rf by sigma 1 into sigma p. So, an interesting way just to, if you want to remember this, then you can just remember this, that ERP minus RF over sigma p is equal to ER1 minus RF over sigma 1. So, this basically this means that is the excess return over the risk. On the right hand side we have this excess return over risk for the asset, and on the left hand side we have excess return over risk for the portfolio. So, this is just a way of remembering. However, we will essentially use this form of the relation. So, so the immediate fallout of this is the following, that this shows that ERP is related linearly to sigma p. Okay. So, you see here that basically E of Rp is a linear function of sigma p, with ER1 minus Rf over sigma 1 being the slope and Rf being the intercept. Now, a couple of observations for the extreme cases. So, if it turns out that if your W1 is equal to 0, then from here we get sigma p is equal to 0, and when sigma p is equal to 0, so consequently E of Rp is going to simply be equal to Rf. And secondly, if W1 is equal to 1, so you go back here, so I get sigma p is equal to sigma 1, then we have sigma p is equal to sigma 1, and consequently from here, if sigma p is equal to sigma 1, this becomes E of Rp is equal to E of R1. And this is sort of obvious, because in the first case, if W1 equal to 0, this means that your entire investment is being held in the risk free asset, in each case obviously the portfolio is going to have a variance of 0, and the return of the portfolio will be the same as the return of the risk free asset, which is Rf. On the other extreme, if W1 equal to 1, that means your portfolio is completely comprising of the risky asset, and so obviously the risk of the portfolio is going to be the same as the risk of the asset, and the return of the portfolio is going to be the same as the return of the asset, the risky asset. So, from here we can conclude that these two lines, these 2 points and these 2 points, they lie on a line. So, that means, so this point 0 Rf, the first pair, and for the second pair sigma 1 E of R1, this pair, they lie on the sigma ER plane. All right. So, next what you need to do is that we can extend asset 1 to the general case of a risky portfolio. So, combining, so this basically means that instead of asset 1 plus risk free asset, the portfolio will now comprise of, instead of an asset, it is just going to be the risky portfolio plus the risk free asset. So, combining the risk free asset with any risky portfolio will obviously result in a portfolio somewhere on the straight line connecting the two. So, this means what? So, this, see, earlier here what we had? We had this relation, it basically the portfolio P will essentially lie somewhere between this on the line connecting this, which is the investment is on only the risk free asset, and this, which means that it is an investment completely in the risky asset. So, that means that this new portfolio, now instead of just considering the risky asset, so just like this statement I had made that 0 RF and sigma 1 ER1 lie on the sigma ER plane. So, instead of sigma 1 ER1 we will consider some generic portfolio. So, this means that, so earlier, so if I consider this to be the sigma ER plane and this is my RF. So, earlier I would have the risky asset somewhere here. Now, instead of the risky asset, now I will consider risky portfolio. So, in this case the portfolio is going to be on the line. So, the portfolio as a result of a combination of a risky portfolio and a risk free asset will lie somewhere on this line when the risky asset is given by A, and of course, here this point is the risk free asset. Likewise, if I choose another portfolio B, then any portfolio combining B and the risk free asset will lie on this line. Now, accordingly, however, this is, you will recall, is the opportunity set for the for a portfolio comprising of only risky assets. But once we have included risky risk free asset, it is basically going to be some combinations like this, and amongst those combination, the one which is highest will be tangent to the efficient frontier of the portfolio of only risky assets. So, this means that earlier the efficient frontier was only this part, and once you add a risky asset, the efficient frontier becomes this part. So, this line RF M bar, that means this is part connecting this, it has the highest return for every level of risk. So, this is synonymous with the definition of the efficient frontier, that for a given level of risk, the efficient frontier is a portfolio that ever at that risk level or the same risk class, the portfolio on the efficient frontier is the one which has the highest return. And a lot of time this M, we use the alphabet M because this is what is known as the market portfolio. So, under some assumptions, it can be shown that this market portfolio actually mimics the real market. So, it is as if that this is just a replication of the overall market from where you can purchase, you have the possibility of choosing any number of assets in the portfolio. So, we can write now, thus we now have a new efficient frontier, namely this straight line. And where all efficient portfolios, that means portfolios which lie on the efficient frontier, are simply linear combination of the risk free asset and the tangency portfolio M. Now, since this efficient frontier is a straight line, it can be described by the following equation, and this equation will come from this equation that I had here. So, it is going to be, so instead of the asset 1, I will have now this tangency portfolio M. So, accordingly we will get the expression E of R P is equal to R F here sigma p, and within bracket instead of E R 1 I will have E R M minus R F over sigma m. So, this new linear efficient frontier is what is called the capital market line or CML. Okay, so now we want to make a couple of observations for this. So, the first observation is that the efficient portfolios between RF and M on the straight line, this involves, so any portfolio this involves lending at risk free rate. So, that means you own a bond. So, this is the situation where 1 minus W 1 is positive, and efficient portfolios above M involve borrowing at risk free rate. So, here this means that in this region any portfolio which lies on this part of the line, this means that you have purchased a bond or lending at RF, and beyond this line all portfolios this will involve borrowing at RF. Okay. So, now let us move on to efficient portfolios with a risk free asset. So, let us look a little deeper on the characteristic of the portfolios that lie on this new efficient portfolio, which is a straight line. So, accordingly we now consider the introduction of a risk free asset to the opportunity set formed with n risky assets. Accordingly, we consider the following problem, and the problem again is going to be since we are looking at the efficient frontier. So, obviously, I will consider the same problem of minimizing the variance, that is, and remember that we had the factor of half. So, minimizing L equal to half W trans W subject to, now remember here I have a risk free asset here. So, it is going to be W transpose E vector plus W F R F, this is going to be E R P, and W F is equal to 1 minus W transpose 1. So, just to justify why have I been doing this. So, here remember this W vector is the vector of weights of n risky assets. So, this means that this term is the weighted sum of the expected return of all the risky assets, plus this is the weight into the return of the risk free asset, and this must add up to the expected return of the portfolio P, which comprises now of the n risky assets and one risk free asset. Further, this W transpose 1 is the sum of the weights of the risky asset. So, if I bring this to the left hand side, this plus WF adds up to 1, and that is how we get this relation. And so, the only relation that I need to look at now is how did I get this to be the same as the variance of the portfolio of risky asset. So, for this we have recalled that sigma p square is going to be nothing but W transpose W transpose sigma W plus W f sigma f square plus twice W f W transpose sigma 1 f, and since this term and this term are 0 as seen already in case of the one asset portfolio, this becomes W transpose sigma W. So, hence while the problem of minimizing of half sigma square should actually be this, but this is equivalent to just W transpose sigma W, and that is the reason why we minimize this objective function. Okay, so, this again we can reconcile with the definition of the efficient frontier, that it is the minimization of the risk for a given level of expected return subject to the weight constraints that we have here. So, let us now move on towards solving this problem. So, accordingly we form the following objective statement. So, as before we follow the we formulate the objective statement that minimize L is equal to half W transpose sigma W plus lambda into the first constraint. Now, what we are going to do now is we are actually, instead of using two constraints, we are just going to merge this constraint into this here, and accordingly I will have just one Lagrange multiplier. So, this will become lambda of E R P minus W transpose E, and instead of W f I will write 1 minus W transpose 1 for this W R f here multiplied by R f. So, we just have one Lagrange multiplier that needs to be ascertained here. Now, applying so where lambda is the Lagrange multiplier. Now, applying the first order condition, and setting equal to 0, we have obtained that del L del W, this is going to be sigma W minus lambda into vector E minus R f vector 1, this is going to be equal to 0, and del L del lambda, this is going to be E R P. So, we are going to recover this constraint E R P minus W transpose E minus 1 minus W vector 1 into R f is equal to 0. Okay. So, now, so we have these two relations now. So, we thus have the vector W from the first relation here, we have this is going to be lambda into sigma inverse within bracket vector E minus R f into vector 1, and for the second one we are obviously going to get E of R p is equal to R f plus W transpose E minus R f vector 1. So, this should be transpose. Now, So we have got these two equivalent relations that we have obtained. So next what you can do is, so we will substitute the expression for the vector w, that is the vector w that I have obtained here, in the relation for expected value of R p, that means this is the in this relation, to obtain the following: E of R p is equal to R f plus lambda into E minus R f vector 1 transpose sigma inverse into E R f 1. Now we define H to be vector E R f 1 vector transpose into sigma inverse E minus R f 1. So, it is this term, and recollect that this E vector sigma inverse E vector, this was B. So, likewise we look at the other terms, we will get twice R f into A. Remember, we have already defined what B, A and C are. So, this expression H becomes B minus twice R f A plus R f square C, where A, B and C already defined. So, A, B and C have been previously defined. So, from here actually we can make a conclusion. So, from here, so now that we have defined this to be H, so from this relation we will get lambda is equal to E R p minus R f divided by this newly defined H. Now, since sigma inverse is positive definite, because the covariance matrix sigma is positive definite, therefore, by definition of positive definiteness, H is going to be greater than 0. So, hence, so now we have the value of lambda. So, hence, the optimal weight for the n vector of risky assets for the efficient portfolio is as follows. So, it is going to be W p vector. So, remember that we had W is lambda sigma inverse E minus R f I. So, this is so I will just write this to be, so I will substitute the value of lambda. So, this gives me sigma inverse E minus R f 1 and multiplied by lambda, which is E R p minus R f over H. So, I essentially make use of this relation, and then in this relation I substitute this value of lambda to obtain this optimal weights. Now, we have got the optimal weights for the n risky assets. So, obviously, accordingly the weight for the risk free asset for the efficient portfolio is W f. Remember, W f is nothing but the vector this 1 minus W p transpose into vector 1. So, here where your W p has already been obtained here. So, further we have, so let me go back to this relation to make an observation that further we have W p is equal to sigma inverse E minus R f into 1 E R p minus R f over H, and this can be written as minus sigma inverse E minus RF I into RF over H. So, I just take this term and multiply here, plus I will have sigma inverse E minus RF I RF 1 into this term. So, then I will get into 1 over H into E of R P. And now I define U to be minus sigma inverse, that is this term, E minus RF 1 into RF over H, and this term excluding ERP to be my vector V. So, this is V is sigma inverse E minus RF 1 into 1 over H. So, here you observe that U comprises of sigma inverse, which is known, E minus RF I, this is known, RF H over is known. So, this is known, and by the same logic V is also known. So, therefore, we can write that W p is equal to vector U plus vector V into E R P. Now, as I have already observed that since the vectors U and V, these are fixed, so the optimal weights that means this W p, these optimal weights for the mean variance efficient frontier can be represented as the linear function, that means U plus V as the linear function of the expected return of the portfolio, that means linear function of ERP. Thus, so this immediately has the fallout. Thus, the two fund separation theorem that we had seen earlier in case of n risky asset also holds for the scenario where when a risk free asset is introduced. So, now we come to another topic that is derivation of the efficient frontier. All right. So, we will look at the two cases. So, let us first begin with the case A, where we have only risky assets. Remember that this was the efficient frontier where you had the curve. So, let the weights of a portfolio P located on the efficient frontier be denoted by W p. Then remember we had sigma p square is W p transpose sigma W, and you remember this W p on the efficient frontier was of the form G plus H into E R P transpose sigma. So, again I replace W p with G plus H ERP, and after some calculations you can show that this is going to be of the form C over D into ERP minus A over C square plus 1 over C. So, here remember that A, B, C and D have been previously defined. Okay, so I leave this calculation to you. Now, in this case, so now we can make a couple of observations out of this. One, so here you observe carefully that I am looking at sigma p square, and here I have a ERP square, because there is a square term at the top. So, this can be interpreted in two ways. So, this is the equation of a parabola in the sigma p square ERP space. So, this means that if we take your sigma p square to be y, so this becomes y is equal to some constant, and this is x minus some constant square plus another constant. So, this is the equation of a parabola. Remember that is equation of a parabola in the sigma p square ERP space. And if we consider the sigma ERP space, then this becomes something like x square, and this becomes y minus some constant square. So, accordingly, this is the equation of a hyperbola in the sigma p ERP space. So, depending on whether you are plotting sigma p square or sigma p against ERP, it will either be a parabola or it is going to be a hyperbola. So, in the sigma p ERP, it is a hyperbola with what is going to be the vertex. The vertex is can be determined from this constant here and this here. So, the vertex is going to be 1 over square root of C and A over C. So, graphically it is going to look something like this. So, I will just look at the sigma p ERP plane. So, here it is going to basically look like a hyperbola, and this point, so we will have these two asymptotes, and this point here is going to be A over C, and this point here is going to be square root of 1 over C. Remember, square root of 1 over square root of C and A over C, this is going to be my the vertex, and here this is also, this point is the global minimum variance portfolio. And further, the equation for this line, so this is an asymptote, this will be given by ERP is equal to A over C plus square root of D over C into sigma p, and the equation of this line here, this is going to be ERP is equal to A over C minus square root of D over C into sigma p. So, here this is the efficient frontier without risk-free asset. So, that is how we know so far we have been actually looking at this type of graph, and this is now a formal justification of why we had taken our efficient frontier of this particular shape. Okay, now it is time for us to look at case B, when we can include a risky asset. So, let us look at case B, which is on the inclusion of a risk-free asset. So, in this case, sigma p square, which is vector W p transpose sigma W p, and this is, you will recall, E minus R f vector 1 sigma inverse E minus RF vector 1, and of course, for with each of these terms we will have the lambda value of ERP minus RF over H, and for both of them this becomes square. So, thus we can write that sigma p can be written upon simplification. So, this is going to be equal to nothing but ERP minus RF. So, just you would recall that this by definition is H. So, this is actually ERP minus RF square over H. So, from this, so combining this and this term, we can write that sigma p is ERP minus RF over square root of H if ERP is greater than or equal to RF, and this is going to be minus ERP minus RF over square root of H if ERP is less than RF. Remember that I always need my sigma p to be positive, and hence this form has to be taken while considering the positive square root of this term. So, this means that this expression above that we have here, this is a pair of straight lines emanating or starting from the intercept RF in which plane? Sigma p ERP space with slopes square root of H and minus square root of H. So, remember that I can here sigma p x like x. So, it is going to be y minus, so ERP minus RF is plus square root of H into sigma p or minus square root of H into sigma p. So, that is how I am saying the slopes are plus square root of H and minus square root of H. So, graphically this looks something like this. So, it looks like, so it emanates from RF, and the equation is ERP is equal to RF plus square root of H sigma p. So, it is this expression rewritten. So, square root of H sigma p, and this is the positive slope, and for the other one, so that means this expression here, this can be rewritten as ERP is equal to RF minus square root of H sigma p, and remember this is the negative slope, because remember that H is positive, and this is in the sigma p ERP plane. So, this is the efficient frontier with the risk free asset. Alright, so now we come to the first last point, which is the tangency portfolio. Remember, the tangency portfolio was the portfolio designated as M. So, you can work out that the weight of this portfolio, so it is a long run derivation. So, I will just state the result, and this is given by sigma inverse vector E minus RF vector I divided by vector E minus RF vector I in transpose sigma inverse 1, and this is sigma inverse E minus RF 1 divided by A minus RF into C. So, this is the weight of the tangency portfolio. So, in summary, let me just do a brief recap of whatever we have done in today's class. So, we started off looking at an extension of the previous scenario where we only had portfolio comprising of risky assets, and now we have considered the possibility that we can include a risk free asset to the existing portfolio of n number of assets, and with that we looked at the determination of what is going to be the weights of the efficient frontier, and we showed that the two fund theorem that earlier was proved in case of a portfolio of only risky assets now holds in case of this situation where a risk free asset is also included. And the last topic that we looked at was looking at the determination of the nature of the curve of the efficient frontier, both in the case when it is only risky assets, and there we see that it can either be a parabola or a hyperbola depending on whether you take the sigma p square ERP space or the sigma p ERP space. And then in case of a risky assets being combined with a risk free asset, the efficient frontier turns out to be a pair of straight lines. And finally, we just noted what is going to be the tangency portfolio that we had seen as the point of contact of the efficient frontier in case of a portfolio of all risky assets, and the efficient frontier with a straight line in case of a risk free asset being included. Thank you for watching.